All right, so these are called coordinate proofs because most of them are going to happen on a coordinate plane. It's not always the case, but for the most part, you're going to do it on a coordinate plane where you're actually going to use these kinds of formulas to demonstrate what you want about a quadrilateral. So instead of like a two-column proof, it's very rigid, and you just kind of follow it step by step. Coordinate proofs just involve calculating values to demonstrate something to be true and one true. And it's a little bit more free form, like you can tell just looking at a two-column proof versus a coordinate proof. There's no structure for a coordinate proof. It's just saying prove that it's a parallelogram but not a rhombus. However you can do that is kind of up to you. There's a lot of different ways to go about it. I'm going to provide kind of a structure for it, but there really is no structure. It's kind of just showing what you know to be true about that quadrilateral, and hopefully it's enough. I really just want to compare the two types of proofs. So two-column proof you're used to. We're trying to eventually show that A, B, C, D is a parallelogram. What's required of a parallelogram? How do we know something is a parallelogram? Two pairs of parallel sides. What else could we show? Yeah, opposite angles are congruent. So you could say opposite angles are congruent. I'm just going to abbreviate stuff. Or you can say opposite sides are congruent. Or you could say opposite sides are parallel. There's other stuff that you can say. We don't need to go through all of them. But you have your choice when you get to a coordinate proof. When you're going through a two-column proof, you don't really have a choice there. You just have to follow those steps exactly. When you're getting to a coordinate proof, you have to decide how do you actually want to prove it, and then do it that way. All right, so I'm going to walk through this the two-column proof first. We're told that BD is congruent to, B and D are congruent to each other, and BC is parallel to AD. So one thing I really like about two-column proofs is the structure's provided for you. You know exactly what direction you need to go with it. Looking at that fourth statement, that's what I need to get to first. BCA, that triangle, and DAC, that other triangle, are congruent. How am I going to get to that? How can I show that this triangle is congruent to that triangle?
Maybe we can say that AC is the same.
Yep, that's the first thing I would do. AC is the same as AC, congruent to itself. By what property? Yep, that's the reflexive property. So now I have that solid. And I have an angle. What else do I need? Yep, that's exactly what I'm going to do. I have parallel sides here. BC being parallel shows that this angle, DAC, is congruent to BCA by alternate interior angles. And once I have that, I have two angles on the side. Kind of just need to think about the order that you're going around that triangle. It's an angle, angle, and then the next side over. So by angle, angle, side, we have those triangles are congruent. Now that I know the triangles are congruent, BAC, I'm just going to label that angle, BAC, and DCA, DCA, those are congruent. Does anyone know why those have to be congruent? Or will we say for the reason that? Say it one time.
I don't know the letters, but I think C.
Yeah, CPCTC. Congruent, corresponding parts of congruent triangles are congruent. If we know those two angles are congruent, from there, then we can show that BA is parallel to CB by alternate interior angles again. That was going to be the converse because we're actually not showing that they're parallel. And now we've shown that we have two sets of parallel sides, so that has to be parallel. Get the exhaustion of that process. I kind of like the structure of that because you know it's kind of just like filling in the blanks. This completely loses that structure, but you don't have to go through these theorems nearly as much. You're now going to use the formulas that you see at the top, distance, midpoint, and slope, to actually just show that this thing has two sets of parallel sides, but it's not a rhombus. We need to show all of that. You could do it in any way that you want. If you wanted to show that opposite angles were congruent, you could do that. If you want to show opposite sides are congruent, you could do that. You could show that opposite sides are parallel. It's completely up to you how you want to do this.
Just go back up.
So it's up to you how you want to attack this. I see that I also want to show that it's not a rhombus. What can you use to show that something's not a rhombus?
It's length.
It's lengths. That's why I would actually use the lengths here. So you could start talking about the sides being parallel, but the slope really won't tell you anything about it being a rhombus or not. So I want to cut my work down as much as I can. So I'm actually going to be talking about the sides and whether they're congruent. So how do you show the length of a side? What formula do you use? Yeah, we're going to use the distance formula. I'm actually going to think about it as Pythagorean theorem. It's the same thing. If you want to use the distance formula between the two coordinates, you can. I'm always imagining a right triangle, though. This to there. I know I can just count directly up and over to form a right triangle. If that's too much, you can use Pythagorean theorem like I'm showing, or you can just use the distance formula. Either way, you should end up getting the same answer. So B to C, that distance, I'm counting 1, 2 up. So that equals the square root of 2 squared plus 1, 2, 3, 4, 5 over plus 5 squared. I'm basically just using the distance formula, just cutting down the showing the work part. So the length of BC is the square root of 29. We're going to do the exact same thing for AD. It shouldn't be surprising. It's going to be the exact same thing. Up 1, 2, over 1, 2, 3, 4, 5. I don't need you to show the work for that. I know you know how to do that. I'm going to say AD is also equal to the square root of 29. And so BC is congruent to AD. I'd like you to number when you have something important. This is one key fact of a parallelogram. I'd like for you to number this. If you don't, I'm not going to like mark you off for that, but I just think it helps you organize exactly what you need to show. That's the first thing I want to get. The second thing is the exact same thing except with the other two opposite sides. So I'm going to show BA and CD are also going to be the same. BA, I'm counting 1, 2, 3, 4 straight down and 1 over. That right triangle has a side of 4 and 1. So that length is the square root of 17. Again, distance formula works to, yeah. 4 squared plus 1 squared. I'm doing the square root of that. That's giving me that 17. Again, it's not a coincidence. CD is going to be the exact same thing. It's also going to be the square root of 17. So now I got those two lines as the same length. So BA is congruent to CD. This is what I mean by demonstrate. I showed the length of those two. I demonstrated that that is a parallelogram. Those two opposite sides, those two pairs of opposite sides are the same. You could have done the exact same thing with slope. If you want to use slope, you can do the same thing. The only disadvantage to that is slope doesn't comment on whether it's a rhombus or not, but we actually do have what we need for a rhombus. BA is not congruent to BC. already demonstrated that. I showed the lengths of both those. I just need to say exactly what I mean. BA is not congruent to BC. That shows everything that I need. It has the two sets of congruent sides, making it by necessity a parallelogram, but the consecutive sides are not congruent, so it's not a rhombus. The lack of structure here can maybe make you feel like what direction are you supposed to go. Honestly, just pick a direction. It's most likely not going to be wrong. You could also talk about the slope going from there to there, and the slope going from there to there is the same. That would show that you have parallel sides. You would just need to do a little bit more work to show that last part. Questions before I jump to the next thing? No, these are the three things that you want to show. It's kind of like this is the reason. This is the reason, and these are the statements. There's just no format to it. We're going to go through a couple more of these. We kind of show that this thing is a parallelogram. Now you have your choice. There's nothing else that we need to show. I would just use slope. When you do this, you could either write it out as like full sentence, the slope of this line is, or the way I'm going to abbreviate this, I'm going to talk about QR, and the slope of QR, we use the letter M. We use it as a subscript there to show that I'm talking about the slope of that thing, not just that line. I'm not talking about the length of it anymore, I'm talking about the slope of that line. You don't need to show all your calculations, you can really just show the answer. The slope of QR, well, that's going down 2 and over 4, so the slope there is negative 1/2. I'm going to do the same thing for TS. TS, again, it's not surprising. Going from T to S, the slope of TS is the exact same thing, also negative 1/2. So that's the first thing I really wanted to show. I have one set of parallel sides. QR is parallel to TS. Do the same thing in the opposite here. Going from S to R. Looks like I'm going up 1, 2, 3, 4. So SR has a slope of 4 over 1, or just 4. Going from T to Q, same thing. T, Q has a slope of 4 also. So SR parallel Q. And that means I'm done. I have one set of parallel sides, I have a second set of parallel sides, that guarantees that that's parallel. If you're more comfortable with distance formula, you could use distance formula. There's other things you could do if you wanted to. This is very easy to me, but if you wanted to show that this is the midpoint of that line and the midpoint of that line, that would also have to be parallelogram, because diagonals have to bisect each other. I wouldn't do that. But if you're looking for a complicated way to prove a parallelogram, you could do that. What do we need to show, sir? Any questions on that one before we go on? What do we need to show for something to be a rectangle? Say one more time, sorry. All of this is the actual answer. This demonstrates this fact. This demonstrates this fact. All of that's required for the actual answer. It's confusing. It's not one number. It's not like a yes or no. It's not as clean as a 2-column proof where it's like fill in the blank, but all of that's necessary for your answer. You can do it in a different way, but you still need to show each of those pieces. What's required to show something's a rectangle?
Two pairs of opposite sides.
Okay, 2 pairs of opposite sides are congruent, which basically just shows it's a parallelogram. What added fact do we need to make sure that it's a rectangle? Yeah, and actually, if we have one 90-degree angle, that's enough. If you have a parallelogram and one 90-degree angle, that guarantees that all of these are 90-degree angles. So we need to show those three things. I'm actually going to list that here. 1, 2, 3. Actually, this is terrible. I want to label this rectangle A, B, C, D. You can use distance. I'm going to use slope. Why would I choose to use slope here? Yep, that's exactly what I want to show. I want to show that these two slopes are going to be perpendicular to each other. So you could use the distance formula and then eventually have to find the slopes anyway, because you're going to have to show that there's a right angle somewhere in here. So I'm just going to list out what I want to prove here. I'm going to try to prove that AB is going to be parallel to DC. I'm going to do the exact same thing for the other sides. AD is going to be parallel to BC. And then I want to show that any two consecutive sides are perpendicular. I happen to put the right angle there, so I'm just going to do it for those two. I'm going to show that AD is also perpendicular to BC. If you can show those three things, you guarantee that it's a parallelogram, and you're guaranteeing that it's a parallelogram with a right angle in it, which means it has to be a rectangle. It could be a square, we don't really care. You know, it would have to be a rectangle. So I'm just going to show a whole bunch of slopes. AB, the slope of that guy looks like we're going up 1, 2, 3, 4, 5, 6, 7, 8, 9, and over 3, so 9 over 3 equals 3. DC has a slope of 3 also. AD has a slope of negative 1/3. And BC has that same slope of negative 1/3. One thing I really love about coordinate proofs, you don't need to justify yourself. Like, we know that these are perpendicular slopes. You don't need to say that anywhere in here. You need to know it, obviously. If you're going to show that these are perpendicular, you need to understand what perpendicular slopes look like, but you don't need to justify yourself saying, since these are opposite reciprocal slopes, we know that these are perpendicular. We're going to assume that we know all of that already. That's really enough. This shows that we have parallel lines. This shows we have another set of parallel lines. We use DC and AD. These two together so that we have perpendicular lines. That justifies the three things that I want to show. Questions before we do one more together? You guys give me a thumbs up, thumbs down, or just thumbs in the middle. Give me just some sort of read on how you guys are doing. Okay, one more together. So take the thumbs down, that's fine. We're just practicing right now. All right, we're going to do number 3 together here. I'm going to plot those 4 points first. You actually don't need to plot them if you don't want to. I would much prefer to look at a picture than try to figure out what's going on there. Number 3, 5. I would also label them with their letters. This trapezoid, or potentially trapezoid. It's called math. We want to show that it's trapezoid, but not show it's but show that it's not an isosceles trapezoid. What does that require? I want to show that it's a trapezoid. What does a trapezoid require? Exactly one paragraph. So you don't just show that we have parallel sides, you also show that the other two are not parallel. we need exactly one pair. So actually, we need two things just to show that it's a trapezoid. We need two sides that are parallel. That's definitely going to be MA and HT. So I'm going to try to show that MA is parallel to HT. I'm also going to show that MH and TA are not parallel. That would show that it's a trapezoid. But trapezoids have four different lengths here, and these are parallel.
Yes, two pairs of parallel lines, but I mean, one pair of parallel lines, but like the opposites.
And these are not congruent? Yeah, that would work.
If you just, yeah.
That's true. That works.
You don't need to stand, they're parallel, right? They're not parallel.
If you say that these are parallel and these are not congruent, you've justified that it's a trapezoid. Yeah. I'm just going to stick with the slopes, although that actually might be faster, because then you won't end up talking about it being isosceles or not. That might be faster. I just see this more straightforward, so I'm just going to do it this way, but you can do it that way. So these two facts are going to show that it's a trapezoid. So M to A, we're going up 6 and over 8. All right, 3/4. So MA has a slope of 3/4. HT truly goes up 3 and over 4. So that's got that same slope. So I've justified the first statement. Those are parallel lines. Actually, now that I'm thinking that is a faster thing. I'd rather do that, but I've already started this. MH is going up 1, 2, 3, 4, 5 and over 1. So MH has a slope of 5. TA has a negative slope, so it's definitely not going to be parallel. Down 1, 2 over 3. TA has a slope of negative 2/3. The last two pieces together justify this statement. Now we know it's trapezoid. We need to now show it's not an isosceles trapezoid. So I'm just trying to show for the third statement that MH is not congruent to TA. Again, you could just use the distance formula with the coordinates if you want. I just think it's easier to think about this as a right triangle because you can really just directly count up 1, 2, 3, 4, 5 over 1. So it's a 5 by 1 right triangle, which means that has a length of the square root of 26. That's MH. I'm going to do the same thing for TA, down 1, 2 over 3. That's a right triangle with lengths of 2 and 3. So TA has a length of the square root of 13. So they are not congruent, so I've justified that third statement also. So it's trapezoid, but it's not isosceles. So I'm kind of setting up a right triangle. You could also just use like the distance formula, but I'm counting from there directly up and over, which forms a right triangle there. Going up 5 over 1, using Pythagorean theorem, 5 squared plus 1 squared is 26. And there's no reason to simplify it. If you want to change this into decimals, you can, but there's no real reason to. As long as you can distinguish that those are not the same number, you're justifying that statement. Yeah, true.
I'm really confused. Could I have like a sheet of paper with some on this and go through it at my own speed?
Well,